The ladder and barn paradox is a pretty well-known paradox. So it deals with having a ladder and a barn, which are the same in length in the real world. But when the ladder is moving through it really quickly, both the ladder and the barn thinks the other object has contracted in length. Now, what happens if you close the barn doors while the ladder's inside it? And of course, the answer that we're typically given is that it's very simple. They disagree on events. So the barn thinks both doors are closed at the same time, when the ladder thinks one door is open while the other door is closed. And they do not close at the same time. Now, this is well and good, but I feel that none of these explanations really kind of show you guys what exactly is actually happening when the doors are closed. I mean, yeah, we get that they disagree on the doors and opening and when they're closing, but what exactly is happening? Can we break it down frame by frame with multiple observers? And that's what I'm here to do. Now, I understand this is more famously known with the ladder, but the other way of looking at it is called the train tunnel paradox. Again, so where instead of a ladder, you have a train. Instead of a barn, you have a tunnel. I'm going to go with this one. And the reason why I want to go with the train tunnel paradox because it's a bit easier to visualize having multiple observers on the same train than just having one ladder and a person running through that ladder with that ladder. So let's take a look at what we're going to see. Now, the setup is very simple. You have a train, and that's the tunnel. Both the train and the tunnel are the exact same length. We're going to say they're a length of 1. Doesn't matter if it's a kilometer or a light year, we're going to say it's a length of 1. And then, all of a sudden, the train is going to move through that tunnel at 0.6 c. So again, this is what the tunnel would see. Again, the train is shorter than the tunnel. And this is what the train would see, where the tunnel is shorter than the train. And again, at one point, both the tunnel doors are going to close while the train's inside it. And we are going to see what happens when that occurs. Now, it's very important to fully grasp this is that we are going to have 2 different observers on the train, not just one. We're going to have observer A, who's at the front of the train. We're going to have observer B at the back of the train. It's with the fact that you have 2 different observers, can we actually see what is going on? Okay, now we are also going to have a stationary frame, which we're going to say that when both the train is completely stationary. Now, we can say that there's 2 ways of looking at this. One, we can say that the train is totally stationary and all of a sudden it starts to move at 0.6 c and it's going to cross the tunnel. The other way to look at it is the train, just before the train hits the tunnel, we're going to have an omnipotent being that's going to see this exact setup right here and see that both the train and the tunnel is 1 distance in length each. And the fact that we're looking at it as if the train was stationary just before it hits the tunnel. It doesn't matter which one. Now, the reason why we're going to have this stationary frame is to kind of help you guys visualize what exactly is happening when the train crosses the tunnel at 0.6 c. So let's take a look from the perspective of the tunnel. So let's assume that just before t equals 0, the train is stationary. At the moment t equals 0 is hit, the train starts to move, and the train moves at 0.6 c. Acceleration is instant. Okay, the first thing is the tunnel is going to see the train contract in length. Now, here's a question here. When something contracts in length, it gets shorter. It needs to contract in length from a certain direction, right? So is that going to contract from the front or the back? See, as you can see here, the base train is 1. Now the train is going to contract to a length of 0.8. Again, because we're moving at 0.6 c, the contraction is to 0.8 distance, or length. Now, when it contracts naturally from our observer as a tunnel, so let's suppose we're on the tunnel, we're looking at the train is going to contract through its center point. Naturally. Again, that's not exactly hard to figure out. It's going to contract through its middle of the train. So in the sense that we're going to see the train shorten by 0.1 from both directions. This is the easiest part to understand here. Notice how before it was 1, and now it contracts to 0.8. It's going to contract from 0.1 from both directions. So we're going to have a small gap between 0.1. Now, remember, before the train started to move, the train and the tunnel were touching. However, as soon as the train starts to move, and it contracts in length, there's now a 0.1 gap between the train and the tunnel. It's this gap that's very, very important. And keep a note of these 2 numbers, 2 0.1s. Again, and this 0.1 occurs twice, and this is going to be important. Now, recall I said that we're going to have 2 different perspectives on the train. We're going to have 2 observers, A and B. A is at the front of the train, and B is at the rear of the train. Now, what exactly would A see at this point? Now, notice how the tunnel sees a gap of 0.1. Well, it's very simple. When an object is moving, and again, we know that so when this train is moving, the tunnel is going to get shortened to 0.8. In addition, not only that, everything, the train track and whatever the world or universe is in, is also going to get contracted from that orthogonal or that direction. So this distance of 2 is originally, again, if the train was just before the tunnel, and they're both 1 each, this total distance is 2, naturally. So from A's perspective, that whatever 2 it saw, 2 distance, now becomes 1.6. Now, this number is not that important, but it's just here to kind of show you guys what exactly is happening. So again, we know the tunnel is going to contract to 0.8. Now, the center point of that length contraction is obviously going to be to the observer. So the tunnel is going to contract to 0.8 from the right to this way. There's no gap. Now, the other way of looking at this, now if you're not convinced, the other way of looking at this is that, okay, suppose that the train isn't moving at all. And we have the left side of the tunnel is 0 distance away from observer A. Now, we know that. The right side of the tunnel, which is the other side of the tunnel, is 1 distance of observer A. Now, if we don't say this is a tunnel, we can say that these are just 2 different signs or something, or 2 different objects. What happens when this length contraction occurs from A's perspective? Well, naturally, the left side, or the left, has a distance of 0. So that contracting down will naturally still be a 0. So that doesn't change. However, the right side is a distance of 1. So when that length contracts, that 1 distance contracts down, it contracts down to 0.8. So now the right side of the tunnel is now 0.8 distance away from A. Okay, so I think this is the hardest thing to understand. So let's just think about it again. So let's suppose that instead of having a left side of the tunnel and a right side of the tunnel, we're just going to have one ruler here, and we're going to have one ruler. And that ruler is 1 distance in length. The other thing we're going to have, we're just going to have a signpost here just before we hit the tunnel. And that signpost is a 0 distance away from A. Okay, and we can also have, let's say, another sign that's 0.1 distance away from A, which is right around here. Now, what happens when A starts to move and that length contraction hits? Okay, the first thing is, we said that this ruler or tunnel is 1 distance away, or a length of 1. Now, when length contraction happens, this 1 contracts down to 0.8, as you can see here. So the right side of this tunnel is now 0.8 distance away from A. You understand that? Now, when we said the left side of the tunnel, what happens to the left side of the tunnel? Again, that left side of the tunnel, where we said it's a sign. So there's a sign on the left side of the tunnel that's the distance of 0 away from A. Now, what happens when that contracts in length? Again, the same thing happened. Because that sign is a distance of 0, the left side of the tunnel does not actually contract, because when you contract a distance of 0, 2 becomes another 0. Now, again, let's suppose you have a sign that's 0. Let's suppose the left side of the tunnel is 0.00001 distance away from A. When you contract that, then again, that doesn't make much of a difference, because that just becomes 0.00008 away from A. So regardless, but notice the important thing here is that notice how there's now an asymmetry in observations between the tunnel and A. And we know there's been an asymmetry because obviously the moving observer is going to look at things differently from a stationary one. And now that difference is now a gap. So the tunnel sees a gap of 0.1 when this for observer A sees that there is no gap. Now, this might be hard to understand, but it is certainly understandable because we understand why a moving observer would see something different from a stationary observer. And we've accepted that when we know that the ladder and barn paradox or the train tunnel paradox exists. But why I'm so emphasizing on this calculation here of this 0.8 is what happens when we look at B's perspective. You see, with B's perspective is what really, really fully explains why all of these things are happening. Okay, so let's look at B's perspective. Now, remember, when something moves, the length contraction is to the observer. So you're on a moving train, you would see length contraction from your own perspective. And your perspective might be different from other occupants of that train. Now, some people are not going to believe that because we're under the assumption that if everyone is on a single frame of reference, how can they possibly see different things? Well, let's take a look at B's perspective. So this is what B looks like if, at the V equals 0 mark. Now, let's look at some measurements. First of all is how far away is the tunnel? Well, the left side of that tunnel is a distance of 1 away from B. Okay? You see that. Not hard to understand. The right side of the tunnel is a distance of 2 away from B. Okay? Not hard to understand at all. Now, let's calculate length contraction to the perspective of B. Okay, so when the train starts to move, that distance of 1, this distance, remember the left side of the tunnel is a distance of 1, is going to contract to a 0.8 towards B. This distance of 2 is going to contract also, but this distance will now be 1.6. So we can see right here. So the right side of the tunnel will now be 1.6 distance away from B, when the left side of the tunnel is 0.8 distance away from B. Here is the thing. A and B see different things. Notice, A sees that the left side of the tunnel is touching it, but B sees that A has already passed the left side of the tunnel. B sees an overlap. A sees they're touching. Now, this gap here would be the reference of So A sees this entire length of tube become shorter, and there's now a gap. Well, again, don't really worry about this gap, but look at B's perspective and A's perspective. A sees that they're touching, but B sees that there's an overlap. Notice how they see two completely different things. But again, if you're not convinced, just do the simple math again. The left side of the tunnel is 1 away from B. So when that 1 contracts to 0.8, naturally, it's going to be right here. But B to A, the distance of the train is always going to be 1, because again, they're on the same train. So they're not going to see their own train is shortening. So A is 1 away from B, but tunnel left, the left side of the tunnel, is 0.8 away from B. So naturally, again, there is this overlap. Take a look at these numbers. All right, next what we're going to do is we're going to see what happens just as A hits this mark here, just before it's going to cross to the other side. So this snapshot is sort of the omnipotent snapshot of what we see if nobody's moving. Again, see A and B fit in, the train fits inside the tunnel perfectly, and now both doors are closed. So let's look at the tunnel's perspective. Now, the tunnel is going to see slightly different than omnipotent perspective because there's length contraction. So that train, which is distance of 1, or length of 1, is contracted to 0.8. But again, the contraction goes to the center. So now there's a gap between both sides of the train and the tunnel. And that gap is 0.1. Again, we saw that earlier, which is 0.1. The other way of looking at it is that from the tunnel, the trains can move a distance of 1, exactly 1, into the tunnel, right? Because that's because the tunnel is 1 distance. When the train moves 1 distance, what happens to the train? Well, if there's already a gap, if the front of the train is a gap of 0.1 with the left side of the tunnel, when the train moves exactly 1, there's still going to be a gap. But now the gap's going to be from the end of the tunnel to the front of the train. Again, not pretty hard to understand. But what's going to happen is that we're going to take a look at A's perspective and B's perspective. And that is where the puzzle gets fully answered. But again, remember, the tunnel sees both doors as being closed right now. Okay, let's look at A's perspective. Now, the first question is A going to see the doors closed or open? Similarly, the second question is B going to see the doors as closed or as being open? So let's look at A's perspective. Now, from A's perspective, again, so what would we know what A would see? Now, if we look at the omnipotent perspective, A is actually touching the right side of the door. But if we look at, or we can go back to here. Now, we know A is touching the left side of the tunnel. We can see here, right? And we're going to see how, first of all we know is figure out how far A is going to travel. Well, it's pretty straightforward. A would have traveled a distance of 1 according to the tunnel, but because of length contraction, A only needs to travel 0.8. Remember the length contraction. So A is going to travel 0.8, which will happen to hit the end of the tunnel. So this is what it's going to look like. Notice B is actually sticking out the back right now. But let's look at A's perspective. A is touching the end of the tunnel, just before the exit of the tunnel. And A still sees the doors as being closed. Now, the door is going to open right at this exact moment, so A can pass through, but A still nonetheless see the doors as being closed. Now, the other way of looking at it is what happens when A approaches that tunnel, is to say, if you're not convinced about that, let's look at it the other way, is what happens when A is approaching the tunnel? Well, then all you do is set the A's travel distance as being 0.79. At 0.79, the door is still closed. Just as A hits 0.8, at that moment, that's when the door is about to open, or when the door opens. But, again, the door is most certainly closed just as A is approaching the end of the tunnel. You could make the argument that the tunnel door technically opens at this moment, but it's still closed at 0.79. I think that's a bit easier way to understand. But let's look at what A sees when he looks backwards towards the end of the train. Now, here's the thing. Because B, or the end of the train, is sticking out the rear of the tunnel, A thinks this door is open. Now, notice, A sees its own door. A sees the door it's closest to as being closed, but it sees the far door as being open. Okay, let's look at B's perspective. Now, B's perspective, first of all, is figure out how far B has traveled. And it's not exactly hard to figure out. B travels for, pretty straightforward, it's going to travel for 0.8, the same as A. So B is going to travel a 0.8 through here. And as you can see, when it travels through 0.8, naturally, it's going to hit the left side of the tunnel. Not hard to figure out. So this is B's perspective. B is touching the left side or the front of the tunnel, the entrance of the tunnel. But B also sees A is sticking out the exit of the tunnel or the right side of the tunnel. But notice, same as A, B sees its own door as closed. Or again, it's about to close or it's closing, but ultimately it sees a closed door. Now, if you're not convinced, let's look at what happens if you put the distance of 0.81, B still sees its door is closed at that moment. But it sees A's door as being open. But notice, B sees its own door as being closed. See, that's the thing. Now, we can make the argument that they disagree on simultaneity, but what's interesting here is that at every frame of reference, they see their own, or both B and A sees its own door as being closed at the same time as the tunnel sees the door as being closed. But they only see the other door, or the door on the far side, as being open. So the three observers do kind of agree on the door being closed. But the two moving observers disagree when the other door is closed.